Hello, Professor. First of all, thank you for letting me do this project on video. Um, so my project is going to be about neuromorphic computing. We're going to compare ANNs, which is artificial neural network, versus an SNN, spiking neural network. We're going to compare its energy and architecture. It's a neuromorphic computing project. Compare its architecture, spiking behavior, and energy usage. A small introduction about this project. So this study compares computational characteristics of artificial neural network and spiking neural network using identical architectures. ANNs perform dense multiplication operations, while SNNs rely on event-driven computation through spikes. So why this project? So the reason for choosing this project is actually very simple. Traditional CPUs and GPUs are extremely power hungry when running an AI workload, especially deep learning models. Okay, they rely on continuous floating point multiplications, and energy cost grows extremely quickly as model becomes bigger. The human brain does not work like that. Okay, our brain communicates through spikes, small electrical pulses. Neurons fire only when they are necessary, which makes biological computation extremely energy efficient. So this has inspired neuromorphic computing. Neuromorphic chips like Intel and IBM True North try to mimic the brain. Instead of continuous activations, they use event-driven spikes. This makes them potentially much more energy efficient as compared to a standard hardware. So the goal of my project is to compare ANN and SNN models in 4 different areas: architecture, spiking behavior, parameter memory usage, and energy consumption. Okay, so basically we want to understand if both ANN and SNNs have the same architecture, how does their behavior change? Does the SNN really save energy, and how different is the computational style compared to a normal neural network? So here is the agenda for my presentation. From the previous slide, we know why is the motivation for doing ANN versus SNN comparison. Next, I will walk through ANN architecture and explain how traditional neural network processes data using dense multiplications. After that, I will introduce SNN architecture and leaky integrate and fire neuron LIF neuron model. Okay, this will help us to see how spikes, voltage updates, and thresholds work over time. Then we're going to look at 100-step energy comparison between ANN and SNN. This will clearly highlight the difference in operational usage between dense computational and event-driven computations. Okay. Following that, I will present the experimental results we obtained from Python simulations, including spike matrices, parameter counts, and energy usage. Okay, and after the result, I will interpret what those numbers mean from an architectural perspective and summarize the conclusions. So why should we compare ANN and SNN? Traditional neural networks, artificial neural networks, ANNs, performs dense computation at every layer. Each neuron in every neuron in every layer participates in the forward pass, whether the input contains useful information or not. This leads to a very high and fixed energy cost. Okay, spiking neural networks or SNNs behave very differently. They are very event driven. Neurons only compute when they receive spike and when they cross a certain threshold. This means no spike means no computation. What I meant to say was, no, if there is no spike, there's not going to be any computation, which makes them naturally energy efficient. So neuromorphic chips like Intel Lohi and IBM True North are built around this idea. They mimic how biological neurons communicate, and they promise extremely low power consumption for AI workloads. So for the goal of this project is to compare ANN and SNN behavior using exact same architecture. We're going to have 3 inputs, 4 hidden layers, 4 neurons in the hidden layers, and two neurons in the output layer. This is how our architecture will look like. So by keeping this architecture identical, we're going to isolate the effect of computational model itself. Alright, so SNN and ANN architecture. SNN and ANN will both share the same architecture. Okay, so the basic idea for both of these architectures is going to be exactly the same, identical. Right, the red dots you can see, this is going to be our input. Okay, the purple is our hidden layer. Okay, it has got 4 neurons. The last layer is going to be the output layer right here, and it's marked with green neurons. Okay, W11, this section right here, is the weight matrix for the hidden layer, which is the purple layer. Okay, and W12 is the weight matrix for the output layer, these 2 neurons. Okay, so as you can see, these 3 weights, these 3 weights are for neuron 1, okay, and neuron 2, neuron 3, and neuron 4. And similarly, we do for the output layer. Each of these weights are connected with each other, but that's the ANN neural network architecture, and similarly, it's the same for SNN. Okay, so now let's talk about the total number of parameters just for the ANN, the artificial neural network. Okay, so as you saw in the previous slide, it's got 3 neurons, the 3 inputs, sorry. So these are our 3 features, are the 3 inputs. Okay, this is the output shape of our input matrix of our input. Okay, this is the output shape of our hidden layer. 4 rows and 1 column. Right, 4 identifies the 4 neurons. Okay, these 4 neurons is the rows. Okay, all right, and the output layer, output shape is 2 rows and 1 column. 2 identifies the 2 neurons right here. These 2 neurons are the 2 neurons we are talking about. Okay, and the parameter shape for the hidden layer, so W1 of 1, the weight matrix for hidden layer 1 is 4 rows, 3 columns. Right here, 4 rows. Okay, 1, 2, 3, 4, and 3 columns. Right. Similarly, the weight matrix for layer 2, W22, is 2 rows, 4 columns. 2 rows and 4 columns right here. Okay. All right. So that's the parameter shape for output layer. Okay. The biases is 4 rows, 1 columns. Each bias for each neuron. So bias 1, bias 2, bias 3, bias 4, right? So each bias for each neuron. Similarly, it's going to have the output layer is going to have 2 biases for each neuron, right? For bias 1 and bias 2, they both have going to have their each bias. Both neurons are going to have each bias, right? And the number of parameters total here is 4 rows, 3 columns, which is 12 weights, plus the 4 neurons, totals 16, right? And here the total number of weights is 2 rows, 4 columns, which is 8, plus the 2 biases, totals 10. So the total number of parameters here is 16 plus 10, which equals 26 parameters, just for ANN neural network. Alright, here's an explanation for an ANN architecture, right? So these 3 represent our input. This column right here is the 4 neurons of our hidden layer. This column right here is the 2 neurons of our output layer, right? W1 of 1 is the weight matrix for the hidden layer. W2 is the weight matrix for our output layer, right? Each neuron is given by this equation, right? This is the activation function of this particular neuron, and this activation function is a function of Z. All right. Similarly, for neuron 2, 3, and 4. Right. Each neuron has its own activation function. Okay. These 4 activation functions, which is A1 of 1, A2 of 1, A3 of 1, and A4 of 1, become the input for our output layer neurons. Right. As you can see here, this one, let's just consider this example. So Z1 of 1 is weight 1, 1 of layer 1. This one at the top means we're talking about our hidden layer, right? So that's what it means. And this 2, let's take an example. This 2 at the top, any 2 at the top, represents, we are talking about output layer. All right. So here you can see W1 of 1 is equal to W1 of 1 multiplied by X1, which is this input. So, and in this case, the input becomes A1 of 1, which is the activation function of our hidden layer. And similarly, we do it for each and every neuron, right? So in the end, Z1 of 1 is the output shape, 4 rows, 1 column for our hidden layer, right? And Z2 of 2, this is 2 rows and 1 column. This becomes the output shape of our output layer. So let's talk about spiking neural network parameters, right? Just like we did for the ANN, we have one for the SNN also. And essentially everything is going to be extremely similar to our ANN architecture and parameters. The only change here is we have 100 here. In ANN we had 1. The 100 here represents the number of time steps, okay? And the total number of parameters is going to be exactly the same as the ANN. I'll just show you again the ANN architecture. This is the ANN, 26 parameters. It's going to be the same for SNN. This 100 is only time step. It does not count to the number of parameters. Everything else is exactly the same. Okay, so here we are at the SNN architecture explanation, right? I'll try to make this as simple as possible. Okay, the entire structure and the way things flow is exactly going to be the same as the ANN, right? I know it looks a little complicated, but I'll try to make it as simple as possible. You can see these 3 dots over here. They represent the input, right? Just like ANN. Okay, this is our hidden layer, the 4 neurons of our hidden layer, right? These are the 4 neurons, and these are the last 2 neurons of our output layer. Exactly the same workflow, right? So let's just consider that one neuron represents a bucket of water, okay? And this bucket of water, how the water inside this bucket represents the voltage, okay? The current that flows, or the water that flows into the bucket, represents the current, okay? It's given by this equation right here, I1T. I'll just explain one neuron, and everything is going to be the same. Okay, so how the bucket is getting filled up with water, it's an analogy of this current right here, okay? When this bucket of water starts reaching its maximum level, the water will spill, okay? That spilling of water is represented by voltage leak, okay? So that equation is given here, the voltage leak right here, okay? How much will the voltage decay, or how much will the water fall out of the bucket, is given by this term called alpha, all right? For our experiment, I had set this to 0.95, okay? But we can experiment with this number as much as we want, okay? So this is the voltage leak is represented by this term right here, okay? So the new voltage is alpha times the previous voltage plus the current coming in, okay? If this value is greater than or equal to our threshold, and we have a threshold value set. We can set it. Okay, so at that particular time the water will leak out of the bucket, or the voltage will leak in our case. Okay, after the voltage leaks, this value goes down and it becomes equal to 0. Okay, and this represents our activation function, which is the function of current, as you can see here. Okay, this activation function right here becomes the input. You can see right here these two terms, weight 1 into the input. It becomes the input for our output layer. Well, I forgot to mention one thing. When the voltage crosses a certain threshold, the bucket overflows, right? The bucket overflows, the water is overflowing. That's our spike. Okay, that's when the neuron is fired. Okay, so in terms of our traditional artificial neural network, the activation is continuous value, okay, like 0.3 or 0.7. Okay, but in our case, in this case, SNN case, the activation is binary. It's either a neuron spike, which is represented by a 1, or it stays silent, which is 0. Okay. So this spike then becomes the input to our next layer, okay, multiplied by the weight, exactly like in the ANN. So the ANN forward pass, okay, the ANN implementation is very straightforward. We perform one forward pass using matrix multiplications. The matrix multiplications you saw right here. So this equation right here, this activation function right here, okay, for the whole hidden layer right here, okay, and similarly for the whole hidden layer, for the whole output layer right here. Okay, so this is the whole forward pass from here to here to here. Okay, this is our output, so that's considered a forward pass. Okay, for our SNN LIF simulation, the SNN is completely different because it works over time. In our case, we have 100 time steps. Each neuron updates voltage and checks for spikes using our LIF equation. Okay, this is our LIF equation. Okay, the new voltage is previous voltage plus the current, okay, plus the input current. If the voltage crosses the threshold, we emit a spike and then reset. Right? The spike matrices. One matrix for hidden layer spike, and then lastly we come to energy counters. For ANN, counting energy is easy. It is just a multiplication in the forward pass, number of multiplications in forward pass. For SNN, each spike triggers a synaptic operation, so energy is directly proportional to the number of spikes multiplied by the number of connected synapses. Okay, this allowed us to indirectly compare energy usage between ANN and SNN for the same architecture using real numbers for the simulation. So for our ANN result, memory and energy analysis. Okay, so layer 1 has 4 neurons, hidden layers, and 3 inputs. So total we have 12 multiplications. I'll just show you the diagram again. Okay, 12 multiplications right here. Okay, and layer 2 has two neurons and four hidden activation layers. Okay, so 2 neurons right here. So 2 neurons and 4 activation which serve as input to the output layer. Right. So 4 2s are 8. So 8 multiplications. So total number of multiplications in our ANN in our forward pass is 12 multiplications for them from layer 1 plus 8 multiplications from layer 2. Total energy cost is 20 multiplications. Because so 20 multiplications, right? Layer 1 12, layer 2 8, so 20 multiplications. Because the ANN performs only one forward computation, the energy cost is extremely fixed every single time you run this model. Okay, that's why the code output shows exactly 20 multiplications for one complete forward pass. So what this means is ANN memory is fixed and it depends only on the number of parameters. ANN energy consumption is also fixed because it always performs the same number of dense multiplications. There is no sparsity, no skipping, or no time dimensions. Okay? Everything is computed every time, whether needed or not needed. And so this result of 20 multiplications for the ANN is going to serve as our baseline when we compare it to an SNN, which behaves very differently as compared to an ANN and often uses less energy due to the spike-based, event-based nature. So let's talk about SNN result memory and energy analysis. Okay, unlike the ANN, the SNN processes information across time. So instead of only one forward computation, the network evolves over 100 time steps, right? The input spike was 93 times. Okay, the hidden layer did spike 69 times. So neuron 1 did spike 20 times, neuron 2 spiked 22 times, 27 times, and neuron 4 spiked 0 times. This is just for the hidden layer. For the output layer, neuron 1 spiked 1 time and neuron 2 did not spike at all. We can change this by changing a lot of settings for threshold, for input current, and all those values. Okay, but just to show an example, this is our experimental results. Okay, so total estimated SNN operations was 510 synaptic operations. This is over 100 time steps, right? So energy proxy, for ANN, energy was counted using multiplications, but for SNN, energy comes from synaptic events. This means a cost is counted only when a spike travels through the weight. Right, so total SNN energy is equal to number of spikes multiplied by number of outgoing weights. Hidden layer has 4 neurons, each with 4 outgoing weights. Output layer has 2 neurons. Over time, spikes activate only when voltage reaches the threshold. Alright, so SNN has the same number of parameters as ANN. The energy cost is extremely different because it only uses energy when spikes occur. It's not continuous as compared to the ANN. This really shows the key principle of neuromorphic computing. SNNs don't compute all the time, they only compute when necessary. This leads to sparse activation and event-driven computations. So overall, the ANN used a fixed 20 multiplications, but the SNN used 510 spike-based synaptic operations, which was spread across 100 time steps. The number highlights that energy patterns are completely different, and ANNs are dense and constant, while SNNs are sparse and time dependent. Okay. So just to give a clear understanding of what's going on right now, okay, so ANN might look like 20 operations, only 20 multiplications, which is quite less as compared to 510 operations for the SNN, the spiking neural network. Okay, and it might seem counterintuitive, but then we have to keep in mind and consider that SNN happens over 100 time steps. So one forward pass for an SNN is going through 100 time steps, while one forward pass for an ANN was only just one forward pass, okay, just one time step. Okay, so just to give a good comparison and make the comparison quite equal, we're gonna just compare ANN over 100 time steps, same as SNN. So if 20 multiplications happened over one time step, over 100 time step, it's gonna have 2000 multiplications. Okay, which is a fully active at each time step. Okay, and over 100 time step, SNN fired only performed only 510 operations. So now you can see an equal comparison between ANN and SNN, and you can realize the energy usage energy and memory usage between both of these models. So on CPUs and GPUs, ANN work extremely well because their processors are optimized for dense matrix multiplications. ANN activates every neuron every step, okay, and that matches the hardware design perfectly. While on neuromorphic hardware, SNN becomes far more efficient. SNNs only compute when a spike occurs, so synaptic updates consume less energy compared to a continuous ANN computation. So in simple terms, ANN is best for traditional hardware and SNN is best on neuromorphic hardware built for event-driven processing. So ANN uses few operations overall because ANN computes only once in one forward pass. These are our key observations from our entire project. Okay, SNN processes information over time, so SNN runs for many time steps and it adds temporal memory naturally. So for the hidden layer spikes which are sparse, even though input spikes are frequent, hidden spikes become sparse and output spikes become extremely rare. On regular CPUs, and SNNs seem expensive because CPUs are not optimized for event-driven computation. So running 100 time steps adds overhead. Okay. On neuromorphic hardware, SNN becomes extremely efficient. A single spike can cost 100 to 1000 times less energy can cost 100 to 1000 times less energy as compared to a floating point multiplication. SNN becomes more energy efficient. Even with the same number of parameters, energy is saved because computation happens only on spike, not continuous. So just to conclude here, what we learned from this project, ANN works extremely well on standard hardware. Because CPUs and GPUs are optimized for dense matrix multiplication, ANN is fast, efficient, and easy to run. SNN provides unique advantage as temporal processing and time-based signals, meaning they are naturally able to handle time-based signals. They also produce sparse spikes, which means they compute only when needed. True efficiency appears only on neuromorphic chips. On normal CPUs, SNN looks expensive because it runs many time steps, but on neuromorphic computers and hardwares like IBM True North and Spinnaker, spikes are extremely cheap. This is where SNNs show 100 to 1000 times more efficiency gains. What this project demonstrated is architectural differences between artificial neural network and spiking neural network, how spikes propagate in SNN versus activations in ANN. Parameter memory usage for both models use 26 parameters, energy consumption for ANN versus SNN, and why neuromorphic computing is more promising in the future. ANNs compute everything, SNNs compute only when needed, and that simple difference is where the energy saving comes from.